And we continue with our second example. Now we're looking at the steady state of our model, the steady state of the model that you can still see displayed on the left side by similarly using the function definition, but now doing it on the whole model rather than just this nonlinear feedback function. Because now we know that the model uses this function, but in the context of this cascade of two consecutive functions. So how will we do this? First thing that we'll need again is, if we want to simulate this, we'll need the set of parameters. So I copy them again over from the model. Now we need to have a function definition as before. So we can just call it our function. Now it's a function that comprises the whole model. We'll need some variable, and we can again call it x, but we actually must consider now an array, namely x is now composed of two variables, x1 and x2, so we need to distinguish between the two. And now we want to use our function definition on the whole thing. How do we do this? If we have a set of functions rather than one function, we put them into square brackets, an array, and separate them by the comma. The second equation is actually rather easy. If you look on the left side, it's just x1 minus x2. So we can very easily incorporate this in here. x1 minus x2. So we have that set up correctly already. Our first thing must have a capital X because we have defined it as a capital X. And we can now check whether we have defined completely. We need to call everything with a capital X. So we have parameter A divided by km1 plus our feedback inhibition ki times x2 to the power of n. However, n is equal to 1, so we don't really use it at the moment. And we have now completed it by saying minus x1. So our first differential equation, which you can see on the left side, is now completely written into our function definition. Our second differential equation also put into our function definition completely, separated by a comma from the first and taken together by the square brackets. Sorry. I want to get a new line. Now we have defined our equation. How can we solve the equation? Well, you have seen in the materials, if you have read through them, that there's something called fsolve, another function that helps you to solve for the steady state of a set of equations, because the steady state means that both differentials are equal to 0. So what we are now assuming is that in our model, all our derivatives, namely the first derivative and the second derivative, are equal to 0. And then, if we solve for the two concentrations of x, this will be the steady state concentration, namely the concentration when there's no more change in the system. So we do this by applying fsolve to our function. Our function is called f, and we need to specify not a range now, but in this case it's initial conditions. We need to assign some value for x1 and x2 such that the solver can start to approach the solution from this initial point on and get there hopefully quickly. Sometimes it's not easy to have a good guess, but of course you can try to combine it with simulations if you don't know where exactly to look. In this case it's not critical. We use this set of initial conditions 1, 1, and if I execute this, I should have a solution which we can look at in our control window. Yes, we can see MATLAB found a solution which is final steady state concentration of x1, which is equal to 3.1127, and the final steady state concentration of x2, which is equal to 3.1127. 0.27. Right, so this is some value, and it's whatever your units of concentration were. That could be, for example, millimole per milliliter or millimole per liter. Now, if we actually go back and look at our equation, you remember what this model looked like. Is it surprising that these two numerical values are identical? Not really, because the way the model is set up, the second equation tells you if the second equation is equal to 0, you can immediately find out that if x1 minus x2 is equal to 0, it means that x1 must be the same as x2. So in this special set of conditions, which we did by putting all rate constants equal to 1, the numerical value of x1 will always be equal to the numerical value of x2. This just as a comment for those who think it's a little bit bizarre. Typically, this will not be the case if you have rate constants other than 1. Right, so we are finished with this solution. We have found our steady state and we have predicted a value. And you can then, of course, change, for example, the parameters and get steady state values at different parameter values. So, for example, if I change the value of a to 2, I can execute this code, and you can see for a double size of the parameter a, you have a different concentration of the steady state values, and so you can do your studies for any concentration and set of parameters that you would like. No, I don't need to do this. I want to close this window because this completes our exercise.